we studied a relation. Okay.
C 可以了，多没？
Okay, roll
C
number.
an zaurem siema. Itu nih keren.
Okay, let's start the class. In the last class, we studied a relation and three types of relation, which are reflexive, symmetry, and transitive. So let me write again for revision. Example, if we have a set A and if we have 1, 2, 3, 4, then if R, okay, for reflexive, this is for just revision. We discussed this in the last class. If AA belongs to R, then it is reflexive. Now, let me write example of reflexive. AA mean a pair which contain both equal term. Here we have 1 1 and 2 2, 3 3 and 4 4, and all are present. Therefore, R is reflexive. R is reflexive. This is important because using this we are going to describe many things, and we are going to solve many solution using reflexive, symmetry, and transitive. Now,
Excuse me, sir.
okay.
2 and 3, sir.
Yes, there could be any other terms here, but if there is 1 1 2 2 3 3 4 4 are present, there could be any other term. But if those pair are present, it is reflexive. Okay. And now for symmetry, if suppose that A, B is present, then BA has to present in the R. Now if we have R, we have 1 1 1 1. If we reverse the order, it is still 1 1. But if 1 2 is present, then 2 1 has to be present in R. If there is no 2 1, then it is not symmetric. But there is 2 1. This is the example. And 3 4. If there is no 4 3, it is not symmetric. But there is 4 3. Therefore, R is symmetric. This is for revision only. This is the rough. And lastly, transitive. Transitive. Okay. And there is one term called antisymmetric. If 1 2 is present and 2 1 cannot present, and all the reverse cannot present except for 1 1, then it is called antisymmetry. So now transitive means if AB and BA are in the relation, then no BC, SC has to be present in the relation. For example, if there is in the relation, there is 1 2 and 2 3, then for transitive, this is B, this is A, this is C. For transitivity, if 1 3 present, then it is transitive. If 1 3 does not present, it is not transitive. Here 1 3 is present, therefore it is transitive. Therefore R is transitive. Equivalence relation. Can anyone remember what is equivalence relation? The definition. Valence relation. I think you studied this in class 11 or 12. So the formal definition is, I will write the formal definition, then we will do some example. A relation R relation is denoted by R on a set A, just like in the example above. We will have a set consisting of some number is equivalent relation, equivalent, not T, it should be CE, equivalence relation. If we have three conditions, three properties, and if it satisfies the three properties, then it is called an equivalence relation. If it is reflexive, symmetry, and transitive. Okay, any question? You can ask about anything: reflexive, symmetry, transitive, also equivalence relation. Okay, before we go through the problems, I will give one more definition, then we will do problems. Partial ordering relation. These two are similar, but there is one difference, so don't confuse with that. A relation R on a set A is partial ordering relation if if not A, R is now the three properties, but it still satisfies reflexive, but this term is different. This will be anti-symmetry and transitive. The only difference between the two definition is symmetry and anti-symmetry. So if you don't have question, I will go through the problem. Okay, problem won't fit in the space, so let me go to the next space. This will be page number 1. So this will be page number 2. Okay. First, we will do problem on equivalence relation. Now we have question. Let us define a set A is equal to 1, 2, 3, 4. Be a set and R is equal to, R is, now we are going to write R in terms of set builder form, is even, so is R in equivalence relation. Now we are going to reflexive equivalent, not reflexive relation. Solution. Now R is defined by A minus B in even, all the pair in which the minus is even. Now, for example, okay, I will give one example. Now, for the pair, let's start with 1. And 1 minus 1 is 0, which is even. So, 1 1 belongs to R. If the minus is even, then 1 1 belongs to R. And the next term will be 1 if 1 and 1 minus 2 is minus 1. Okay, for remember, even number is number divisible by 2. So 0 is divisible by 2. So 1 minus 2 is not divisible by 2. Now 1 and 3, 1 minus 3 will be minus 2, which is divisible by 2, and so on. And now you go to 1 and 4. 1 minus 4 is minus 3, which is not divisible by 2. And can you tell me the next term? 2 and 1
2
is not.
2.
Yes, 2 and please go on.
2 4.
2 4. Then
3 1. 3 1.
3 1.
Then 3 3.
3 3. Yes. Then
And 4 2.
and 4 2.
And 4 4.
4 4. Yes. We have to find that if this is equivalence relation. Now first we have to find if it is reflexive. So reflexivity. Now by looking at ER, can you tell me if it is reflexive? Anyone?
Yes, it's reflexive.
Why is it reflexive?
Because
4. There
it
is
is
4.
1, 2, 2,
1 1 2 2 3 3 4 4 at
3, 4,
present.
4.
Yes, very good, both of you. Because since 1 1 2 2 3 3 4 4 is present in belongs to R. Therefore, R is reflexive. Now, secondly, symmetry. So, is it so to check symmetry? Now we have to find.
Yes, sir.
Yeah, 1 1. We will not write 1 1 because it is clear that if we reverse this, it will still be 1 1, and 2 2 also this. If we reverse this, it will also be 2 2 and 3 3 and 4 4. By symmetry, it is obvious that the reverse is belongs to R1. So let's start with 1 3. 1 3 belongs to R. Is it the reverse belong to R, the reverse order? And for symmetry, AB belongs to R implies BA. So if we reverse this, then here we have 1 3. If we reverse this, 3 1 is belong to R. So both are the reverse order also belong to R. And for 2 4, 2 4 belongs to R, and 4 2 belongs to R. So now all the reverse, if we reverse all the term, then it will still belong to R. Therefore, it is symmetric. Therefore, R is symmetric. Now, lastly, we have to find out transitivity. Transitivity. By properties of transitivity, if A, B, and BA belongs to R, BC belongs to R, then AC must belongs to R. If it belongs to R, then it is transitive. It does not belong to R, it is not transitive. So let me take any two number which belongs to R. Any two. So we can take 1, 3. Okay, for example, if we take 1, 3 belongs to R and any number we start with 3. So there is 3, 1 and 3, 3. Any one. So if we take 3, 1 belongs to R, and now here AB and BC belongs to R, which implies that AC, the first and the last term, belongs to R. Now 1, 1. Now we look at the first and we take the first and the last term. Now we look at R, then here 1, 1 belongs to R. So it's satisfied for other term. It is also true. We will not write all the term because it's going to be lengthy. It is also true for all other elements. Therefore, R is transitive. So let's go to the main question. Is R an equivalence relation? So can you tell me, is R an equivalence relation? Is it equivalence relation or not? R
Yes.
is okay, and equivalence relation. Okay, any question? Hello, Iris. Okay, I'll assume that you don't have question. So here, these questions are easy when if the set is defined like this. A is equal to 1, 2, 3, 4 because there is only 4 elements in A. It is easy to calculate that. So let me give another example in which A is defined on infinite set. That is the number of set in A is infinite. So this is page 3. Then let's go to question. So we will define on let Z. Z will always denote the set of all integers. So the set will be Z, which mean that it is not just 1, 2, 3, 4. It will be all the 1, 2, 3, 4, 5, 6, and go on the positive side, and negative side it will go to 0, -1, -2, up to infinity. So let Z be the set of all integers. Okay, I will write this anyway. Z from Z, there is in negative side, there is up to infinity also in the positive side. But it does not include some decimals. So R is equal to, since Z is the number of elements in Z is infinite, we cannot just write all the component of R because we cannot write infinite element. Here let's define by R is defined. The definition of R is same as the previous question. It look difficult, but if you give attention, it is not that difficult. Valence relation in Z. Now proceeding as before, first we check reflexivity. Okay, we in here we don't know, we cannot calculate for all the properties of elements. So we take some random element from Z, and if it satisfies the properties, we will assume that all the elements from Z satisfy the property if we take one random element. So let's take A, B, and arbitrary. It could be any element of Z. R, not this, arbitrary. Arbitrary mean if we take some random element of Z, which could be anything inside Z, then we know that here A my reflexive is with itself. So we write A minus A. If so, what will be the value of A minus A?
0.
Okay, very good. 0, and 0 is even, and any negative number is can also be even, like -2. So this which means that which is even. So A is an arbitrary. So which means that any elements we can, for any elements of that, this is true. So we can write for all A belongs to Z. This is for all. So it is true for all element of Z. Therefore, R is reflexive. So number 2 is symmetry. For symmetry, we know that A, B belongs to R. If A, B belongs to R implies BA, AB, whenever AB belongs to R, then BA belongs to R, then it is symmetry. Now we assume that let A, B belongs to Z, which means that, okay, let's write in words so that it is easier to understand in what is any element or an arbitrary. Let's write an arbitrary. We used this before. Arbitrary element of Z. In symmetric, first we assume this property is true, such that A, B belongs to R. From the equation that A, B such that A minus B is even. All the element of R, if A, B belongs to R, then it means that A minus B is even. This, which implies that is even. Like I said before, if B minus A is, if 2 is even, minus 2 is also even. So so if we take negative as common, this will still be even number. So if minus 2 is even, surely 2 is even. So if we remove the minus sign, it will still be even number. So here we start with AB belongs to Rn and with BA belongs to R. The reverse order, then it is symmetric. Therefore, R is symmetric. If you have a question, you can stop my explanation. Just ask anytime you feel like asking a question. And properties number 3, the last property is transitivity. So in the transitivity properties, we have A, B, and B, C belongs to, whenever A, B, and B, C belongs to R, then the first and the last term, AC belongs to R. So we will start with that A, B, C, R and R are three elements of Z, such that, so we have two conditions. A, B belongs to R and B, C belongs to R. This implies that A minus B is even and B minus C is even. Can anyone tell me that if we add two even number, is it even? The answer will be even or odd number.
Even, sir.
Even.
Okay.
Even, sir.
Yes, very good. If we add any number, this is even, this is even. So if we add this will be even. So A minus B plus B minus C is even. So if we remove the bracket, this will be B even. So it is minus B plus B. So what will be this term? Can you tell?
A minus C.
No, let's forget other term. Like this is an integer, like minus 5 plus 5. What is the value of this?
0.
Okay, so this is 0 and this will be 0. So we can ignore 0. So which means that A minus B is even. If A minus C is even, then AC belongs to R. We start with AB belongs to R and BC belongs to R, and ends with AC belongs to R. Therefore, we have R is transitive. Since R is reflexive, symmetry, and transitive, therefore R is an equivalence relation. Please mute your mic. Equivalence relation. So I will give one problem in equivalence relation, which will be for one of your question in your assignment, but you don't have to submit now. I will write this question, which will be part of the assignment for later. So let me write this question. You can write it down, or you can just screenshot also. Let's just be the set of all integers and let R be a relation in Z defined by, here the question is same, Z R, only R will be difference. The difference will not be very much. A minus B is even, mean A minus B is divisible by 2. Now it will be A minus B is divisible by 5. So that R is an equivalence relation. Okay, I will give you 10 seconds if you want to write down or screenshot this. This will be one of the question in your assignment, but you don't have to submit now. I will say in the later class. Okay, before I move on, is there any question?
No,
Okay,
sir.
okay, very good.
Sir,
Yes,
I don't find the link of Google Classroom.
yes, I have not created Google Classroom. Yes,
Okay.
do you use Google Classroom in every class
Yes,
or
sir.
every class?
Yes, sir.
Okay, okay. Maybe I'll provide it later. File. Today is 2 class period, but I think I can end at 4, around 4. So now let me go to the next question. Now let me give example of the partial order relation. Another, this is page number 4. In the partial order relation, it is first it is reflexive, then it is not transitive, but it is not symmetric, it is anti-symmetric, and it is transitive. The difference between anti-symmetric is that when the reverse, okay, I will explain on the solution. First, let me write the question. Let A, this is equal to 1, not 1, let's start with 2, 3, 4, 5, 6, 7, 8. And R is equal to AP such that A is a multiple of B, which means that A is a multiple of B, means that A will always be bigger than B or equal to B. So that R is partial order relation. So the solution, the step is same as before, but we have to find reflexive, anti-symmetric in place of symmetric, and transitive. Here it is not infinite, so we can, there is only 7 elements, we can write the value of R. Here all the pair such that A is multiple of B. Let's start with the biggest one, 8. So 8 is a multiple of 8. It is clear. Now 8 is also a multiple of 4, and 8 is a multiple of 2. And let's start with 7. 7 is on a prime number, which means that it is only divisible by itself and 1. And 6. 6 is divisible by 6. 6 is divisible by 3. 6 is divisible by 2. 1 is not in the set, so we don't write 1. And now 5. 5 is also a prime number, which means that it is only divisible by itself. And let's write this. and 4 is divisible by 4 and 2, and 3 is also a prime. 3 is only divisible by 3. Also 2 is a prime. 2 is divisible by 2. So this is our number 1. We have to find if it is transitive. So the process is called transitivity. So can you tell me if it is transitive? Can anyone?
No, it's not transitive.
What is that? Okay. Let's start with reflexive. If it is, can you tell me,
No.
is it reflexive? What is that?
Yes, sir.
Yes, it is transitive. It is reflexive because all the elements 2, 2, 3, 3, 4, 4, we can find 5, 5, 6, 6, 7, 7. All the element paired with itself is R belongs to R, so it is reflexive. Therefore, R is reflexive. Number 2, anti-symmetry. So here, to be symmetric, we have both 8, 4 and 4, 8 have to present in R, but here only 8, 4, 8, 2 and 8, 2, 8, 4 is present, 4, 8 is not present. 8, 2 is present, 2, 8 not present. 6, 3 is present, 3, 6 is not present. 6, 2 is present, 2, 6 is not present. Similarly, 4, 2 is present and 2, 4 is present. The only element in which we can reverse the order and still belongs to R is that in 8, 8, in 7, 7, in 6, 6, in 5, 5, 4, 4, 3, 3, 3, 2. That is, which means that by definition of that A, B belongs to R implies B, A belongs to R if and only if A is equal to B, which means that both the terms are only when both the terms are equal, then which means that it is antisymmetric. So now, now it is clear that let's write in what? Clear that AB belongs to R implies BA belongs to R only when AB belongs to A, no, not belongs to, A is equal to B. Therefore, R is anti-symmetry. Now let's take transitivity. We can start with the first one here. No, 8, 8. 8, 8 belongs to R. Here in the transitivity question, AB belongs to R and here BC belongs to R. So this last term and this first term has to be equal. So let's take another element which start with 8, which means that the second or the third, we can take any one. 84 or 82. So let's take, okay, we can take any one, 82. So which if this implies that AC belongs to R. If we take the first and the last, which is still 84, and it still belongs to R. Let's take another element. You can pick any one. Who want to pick it? Okay, there is no other element like this. Only, okay, I think it is clear now. Let's not try another. So this is true for all the elements in R, which is also true for elements of R. Therefore, R is transitive. So it is antisymmetric, transitive, and reflexive. Therefore, R is partial order relation. Any question besides this? If you don't have question, I will move to the next definition. So this is for relation. Now we can go to lattice. In lattice, I will give around 6 definitions. So then we will stop the class. So I think you may have studied boundedness. You may not studied it. I don't know. So I assume that you don't study boundedness in before. So I will explain this with example, but I will write the formal definition first. Boundedness. Okay, let me write the subtopic only. First definition will be bounded above and upper bound. I will give two definitions in one statement. A subset S of real number. Here, a subset S of real number means that S will only contain real number, and it cannot contain other number than real number. Other number than real number is complex number, and there is imaginary number. So it cannot contain any other number. Real number S is said to be bounded above if there exists. This sign means that there exists. This is a symbol for, maybe this is the first time you heard it, maybe not, but I will write it. There exists a real number K such that every member of S is less than or equal to K. That is, X is less than or equal to K. This symbol is for all X belong to S. In mathematics, sometimes it is difficult to understand from the definition or the statement. So I will explain this using example after I give one more definition. Here, K is called an upper bound of S. Here I use not D, I use N upper bound, not the upper bound. Which means that there can be more than one upper bound. So which I will explain later. Well, let's give one more example. Bounded below and lower bound. The set S is said to be bounded below if this sign is there exists a real number K such that every member of S is greater than or equal to K, that is K is less than or equal to X for all X belongs to S. This symbol is for all. K is called a lower bound of S. Now I will explain. It is quite easy. It is easier than it looks. So let me give one example. Let me write a set A which consists of numbers. Okay, let me call out one name. Lazui Tuanga CE. Is he here? Lazui Tuanga.
Yes, sir.
Okay. Okay. Say any number, any 5 number.
1, 2, 3, 4, 5.
1, 2. Okay, good. Thank you. First, we will look at in the definition, we use the word S. So for this time being, I will replace this S. It can be any number, but in the definition, I use S. S is said to be bounded above if there exists a real number k such that every member of S is less than or equal to k. Here we look at S if we take for k is equal if k is equal to 11, then every element of let me write. Let me write that below. For k is equal to 11, from the definition, every element of S is less than or equal to 11. So every element of S is, this is from the definition, less than or equal to 11. So k is an upper bound. So you may wonder why we choose k equal to 11. We did not choose k is equal to 11. We choose one value where it is one value of upper bound. So there can be any upper bound. So let's write if we take k equal to 12. So all the terms are less than 12, 13, and so on. So all these terms are also upper bound. So when I choose k equal to 11, I only write one upper bound. Are all upper bound of S. I think it is clear by the name. So from this, I think you understand what is lower bound. So can anyone tell me one example of lower bound?
1.
Okay. So one. Can you give another?
2, 5, 6, 7.
No, two. Lower. If we take 2,
Minus 1.
yes, minus 1, it will go downwards now. 0, you can take 0 also, and like that are all lower bound of S. There are some set which are not bounded above. So I will give example, another example. Example, the set of natural number is bounded below, but not above. So natural number is denoted by n. So can anyone tell me what is natural number?
Numbers start from 1
Yes.
to infinity.
Yes, very good. So it is not bounded above because it goes on like that. And it is bounded below. There are number less than 1, which are 0, minus 1. It is also bounded by 1. So there, like this, there is we can give sets which is bounded above, not below. So if it is bounded above and bounded below, like this set is bounded above and bounded below. So these sets are called, okay, these sets are, we say that S is bounded. So if it is both bounded below and above, we say that it is bounded. So let's write this. Not a set is said to be bounded if it is bounded above as well as below. So from this example, we know that there are many upper bound of S and there are many lower bound of S. So one more definition. If the set of all upper bound. In the first class, we define set as collection of objects. So you may imagine like the collection of all upper bound. So you can understand better. If we take all the upper bound of a set, if the set of all the upper bound of a set S has the smallest member, it is called okay, if that number is M is called the least upper bound or supremum. This is number one. Similarly, for lower bound, if the set of all lower bound of a set S has the largest, in the smallest is replaced by largest member. Let's say that this is small m. Say m. Small m is called the greatest lower bound or infimum. So I will read again the first definition. If all upper bound of the set S has smallest member, then it is called this upper bound. So let's look at the first example. So we have the set 1, 2, 3, 4, 5, 7, 9, 11. So it has upper bound, which are 11, 12, 13, and go on. If the set of all these upper bound, all the upper bound has a smallest member. In this case, among the upper bound, 11 is the smallest member. In this case, 11 is called the smallest upper bound, least upper bound, or infimum. 11 is least. Sometimes they just write it LUB. 11 is LUB. Here in this, similarly, in lower bound, here it has lower bound 1, minus 1, 0. Among the lower bound, 1 is the largest. So it has greatest lower bound. So 1 is greatest lower bound or infimum and supremum. So do you have a question? There's only one definition left for this class. I will give one more definition.
Excuse me, sir.
Yes.
Can I note the definition last part? I
Okay.
haven't completed.
Is this one?
Yes, sir. Oh,
In the meantime, let's save this first. This is page number 5.
I'm
Kijen,
done,
do you
sir.
finish? Okay, okay.
Yes.
File, new. So this is page number 6. This write the last definition for today. This now we will go to lattice. So a lattice is a partially ordered set. Okay, actually we need 2 more definitions because we have not defined what a partially ordered set is. So after this, I will write one more definition. A partially ordered set in which every two elements have a unique list upper bound and a unique greatest lower bound. So I have not defined a partial order set, so I need that definition. So let's write right away. Now partially order set. We already defined a partially ordered relation, which is reflexive, antisymmetry, and transitive. Now it is a set. A set A together with a partially ordering relation are on A is called a partially ordering set denoted by AR. When we define partially or ordering relation before, we write R, the relation Rn, we define on a set A. So if we write together, we take together as one thing, AR. If we say together at the same time, then it is called, the set is called a partially ordering set. And a partially ordering set is sometimes called order set. Is also not some, let's write it, also known as aka both set. B is partial, O is order set. So I will write one more para under partial order set, because we will use relation, a specific type of relation which is less than or equal to. Order set is denoted by and A, and this is less than or equal to. So there is a definition within itself. Let A is a partially ordered set. A, this should be comma, this should be small, a subset of A is called a chain if every two element in the subsets are related. Okay, this is the definition. I think enough information for today. I will explain this and lattice in the next class, or I think I already explained partially ordered set, which is not difficult. I will explain lattice in the next class. Okay, I think we can end now. So if you already give your attendance, you can leave. So for those who do not